So for today, we're going to finish up talking about some exponentials and radicals. So we're going to finish up 1.2. Even though it says 1.3, we got to finish a bit of 1.2, then we'll go into a bit of 1.3. So the last thing we talked about was, hey, if I have a number raised to the 0 power, we can express that as 1 or evaluate as 1. And the reason why that's possible, say we take the number 3 squared. Well, if I'm going backwards to the first power, I'm going to be dividing by 3 instead. So then I get 3 to the 0 equals 1. So then the question is, hey, great, I can do all that, but what is a to the negative 5th power? Well, if I keep dividing this out, let's go to negative 1. I get 1 divided by 3, which is 1 divided by 3. I get 3 raised to the negative 2nd power. Well, if I divide that by 3, that is 1 over 9. But there's something even more useful than writing as 1 over 9. I can rewrite this as 1 over 3 squared, because 3 squared is 9. And then you see the connection. It's like, oh, look at this. Hey, whatever the negative exponent is, we're going to have 1 over that value, and it's a positive exponent. So if it's a raised to the negative 5th power, I should have that as 1 over a to the 5th power. Great. Now, what happens if we have 1 over a to the negative 5th power? So what are we actually doing? Well, we know we're dividing by a. However, this time we're having 1 divided by a again. So that gets a little confusing. But if you ever recall, then maybe you might have tried this out or not, but when you divide by a fraction, if you were to divide by 1/2, what are you actually doing? Well, if I divide by 1/2, dividing by 1/2, that's the exact same thing as saying multiply by 2. And why is that true? Well, we just move the 2 upwards, because if I divide by a divide, this is a division symbol, it turns into multiplication. Then I can say 1 over a to the negative 5th power is the same thing as saying a to the 5th power. Or you can say a to the 5th power over 1. Same thing. And we got a few definitions. This was our first one. Then we could say that, hey, if I have b, ab raised to the 3rd power over, let's say, I don't want to do that. Let's say c over here. Well, in this case, let's do c to the negative 3rd power as well. None of these bases are the same. However, because it has a negative exponent, all we simply have to do is move them to either top or bottom. If it's on top, we're going to move it on bottom. If it's on the bottom, we're going to move it to the numerator. So in the case b raised to the negative 3rd power, the negative exponent is on the numerator, we're going to move that entirely to our denominator, b cubed down there. C to the negative 3rd power is in our denominator, so we're going to move that to our numerator. Boom. So that works out nicely. Then we have that down. Now we got to think about, hey, some properties of negative exponents. Okay, properties. Before we get into the properties, we need to be able to do powers of fractions. So I have a over b raised to the c power. Well, that's a over b times a over b times a over b, which if we multiply fractions, we're only multiplying the top row. So we get c amounts of a times a times a times a times a, c times. Same with the bottom. So if we have that down, then we can write some properties with negatives. What happens, the first property, what happens if we have a over b raised to the negative c power? Well, that's the same as saying we have a to the negative c over b to the negative c, which that's going to give us b to the c over a to the c. Because they have negative exponent, they have to move from bottom to top and top to bottom. So that's what happens. Now let's do an actual example with some numbers. 3x over y cubed to the negative squared. Well, for this problem right here, we have to think a bit. Okay, let's follow the same rule here. Do not get scared. Treat the 3 like some sort of variable. Well, the variable should be treated like a 3, I guess. But we can use that as a placeholder. So if we follow the exact same definition we have earlier, we have 3 raised to the negative second power x. Now, power to a power states that we multiply the exponent, so we have negative 6 over y negative 2. Now we move them around. Well, all of them have negative exponent, so we're just going to swap all of their position. Now, of course, in a test setting or anything, I want you to calculate 3 squared. You can do that, but for now, I'm not going to write that down, but we all know it's 9 in this case. Or you can at least calculate to show it's 9. So that's the example there. Boom. Now, let's get into another topic, radicals. So, calculating radicals, what are radicals, all of that stuff. So, this symbol right here, this is a radical, but we also call it a square root. That's misleading though. There's some ambiguity with that. So, mathematicians don't tell you this, but we all know it. So, I'm going to let you guys know what we're talking about. When you have a radical and there is no index, I'll talk to you what an index is. There's no index. Assume that there's a 2 in that position. This position right here, assume is 2. You assume it's 2 if nothing is there. And this is called our index. The index of a radical is important because it tells you how it operates. So if you don't see anything, assume it's square root, unless otherwise stated. Then, if we make that assumption, I'll just keep it as square root because we're familiar with that for now. If I say square root of a, by definition, we're going to treat that as, hey, there exists, I don't know what number it is, there exists some number raised to the square power, second power, that'll give me that value a. I don't know what that value is, but some number raised to the second power should give me a. It could be a real number or whatnot. And then let's look at this concretely because this can be confusing. Example, square root of 9. Well, the square root of 9, you guys heard this before, is equal to 3. But this means that 3 squared is equal to 9. There exists some number that if I square it, I get 9. Find this guy. And notice that this 2 is the same as this 2. Index power. Great. So we have that now. Well, now we gotta be able to do some things that are more complicated. Instead of using 2's, we gotta talk about what if it was just some other number n. Well, we just follow the exact same thing. Oops, sorry about that. Exact same procedure. This implies that we're gonna have some number b raised to some n power is gonna give us that a. Okay? So you don't have to just do square roots. If you do any number than 2, we have different names for it. So we'll call it the nth root, or sometimes your book says the nth principal root. It could be the second root, third root, fourth root, fifth root, sixth root. Now, 2 and 3 have special names, square root and cube root, but generically we can just use numbers for those nomenclature. So we have that. Great. How does this relate at all to what we just talked about? Well, that goes into the next topic. Radicals to exponentials. I'm going to show you this, and then I'm going to talk about the properties of radicals, because you're going to see the relationship between this. So radicals to exponential. Let's start off. If, let's say, n, I'm just going to do ab, raised to some m power. All right. If I'm going from radicals to exponential, your index is your denominator. Oops. This will be your denominator, index. And this will be your numerator. So whatever's inside our radical will be the base of our exponential function. Make sure you put the parentheses. You need the parentheses. And now it's going to be raised to some power, some fractional power, or ratio between the index and the power inside the radical. So the index will be our denominator, and the power inside the radical will be our numerator. So for instance, if I have the cube root of, let's say, 5 squared, that is the same thing as saying, hey, I have 5 raised to the 2/5 power. So that's how we turn radicals to exponentials. You can go backwards as well. Your base is always what's being raised to the power inside the root. Your numerator is the exponent inside that radical. And then your denominator is always your index. So keep those in mind. Moving forward. Now, we can talk about the properties of radicals. We make two main assumptions with radicals. The index, if I don't show any index at all, we assume that guy is 2 if it is not there. We also assume it's positive, kind of like the number 3. We don't say plus 3. If we just see a 3 by itself, we assume it's positive. So, some properties. Hey, property 1. We have, let's say, AB, the nth root of A times B. That is the exact same thing as saying, hey, I'm doing the nth root of A times the nth root of B. Why is this true? Well, if you don't believe me, let's go back to the exponential world. If I put the first thing in the exponential world, well, we know that AB doesn't have an exponent, so we're going to assume the exponent is 1. So assume the exponent is 1. Well, that means our power is AB raised to the 1 over n. Our index is our denominator. Well, to deal with exponents, and they're multiplying it out, you just put the exponents on the A and the B. So it's going to be A raised to the 1/8 power times B raised to the 1/8 power. Well, they're the exact same thing. They are the exact same thing, so it checks out. This property does hold. Property 2. What if we had nth roots of A over B? A fraction inside my radical. Well, this is simply going to be the nth root of A divided by the nth root of B. Why is that true? Let's go to the exponential world. Well, if I go to the exponential world, this guy is the same thing as saying A over B raised to the 1 over n. And that's the same thing as saying A raised to the 1 over n, B raised to the 1 over n. It checks out nicely. All right. Third property, which is the final one for this. So my square root, or my radical, if I have an nth root and my term inside this radical is raised to the nth power, what do you guys think that's going to be? Well, some of you guys might have said A. And I'm going to say you're kind of right, you're kind of wrong. So I'll write A over here. Let's do the process. If I turn this to the radical world, I get A to the n raised to the 1th power. And a power raised to a power, we're going to multiply that. So we're going to do A to the n times 1 over n, which is A n over n, which is equal to A to the 1st power, which is equal to A. So it does look like it is A, but there's a problem. When we do our mathematics, you always have to consider the domain of your variable. What does that mean? I have to consider, hey, what is the letter A? Is it a real number? Is it a decimal? Is it a negative number? It is important. And I'm going to show you why. So let's go over here and let's do a concrete example. Let's do square roots, 2. Let's do 4 squared. 4 squared is 16. What is a square root of 16? Well, that's going to be 4. So it looks like the values, A and A, do match up nicely, right? Or at least you would think so. Now let's try a different one. Let's do this. And I put parentheses because I want to do the negatives first, and then I want to square it. Negative 4 squared. Well, negative 4 times negative 4, a negative times a negative is a positive, so that's 16. But we just showed the square root of 16 is 4, so this has to be 4. Wait a minute. This guy does not match up with this guy, does it? It looks like we always get a positive answer. Well, let's refer back. What symbol, function, / operation do we always use to turn our answer positive? If you guess the absolute value function, you are correct. So, must be positive. This must be positive. Must be positive. You cannot have a negative number if n is even. If your exponent is even, you will always have to have a positive answer at the very end. So if you plug in a negative number, you will get a positive answer for A. So we can say that the other condition is if n A raised to the n, if n is odd, this is equal to just A. If n is even, it has to be the absolute value of A. If n is odd, it's just whatever you plugged in for A. It could be that negative number as well. And I encourage you to try that out, and you'll see why that works. Moving forward. That covers the properties of radical. Now we need to know how to deal with them with numbers. So, let's deal with some numbers. Let's do the square root of, this is called factor tree, or simplifying radicals / factor tree. Let's say we did a square root of 24. Square root, assume there's a 2 there for now. Well, to do the factor tree, a factor tree is breaking up the number you have. You're going to break up the number into factors or pieces of the product. Product is multiplication, so what multiplies to get to 24 besides 1 and 24? And if I break up 24, I can multiply 12 times 2. That works too. I can break up 12 into 6 times 2. I can also break up 6 into 3 times 2. Now, I broke it up in this manner. Notice that I did not try to break up 2. The only things I can multiply, the only natural numbers I can multiply to get a 2 are 1 and 2 in itself. If that happens, we call that a prime number. Prime numbers are numbers that the only factors are 1 in itself. And I can't break them up anymore. So, my prime numbers in this case are 3, 2, 2, 2. That's the end of my tree routes. So, I can actually re-express this as, believe it or not, 24 is equal to 2 times 2 times 2 times 3. All your primes. It actually works out. You can test it out with the calculator. Now, the key thing is, this is a square root. So there's a 2 assumed to be there. Now, what does this 2 have to do anything? Because so far we've done roots, but I haven't shown you why it's useful or what it does to our problem. Well, it turns out that when we're dealing with square roots, the only way we can simplify this nicely is to know our index. Our index will determine how we group our prime numbers. In particular, because the index is 2, we want to group in pairs is 2. We want to group pairs of the same number or the same prime numbers together. So the only pairs I have are this one over here. However, there are no extra pairs for the number 2 and 3. They are isolated. What does that mean? Well, if you get a pair, you get 2 squared times 2 times 3. Correct? Well, going back to our other definition, this says 2 squared right here, and this says 2. If we go back to our other definition over here, it says, hey, if they have the same index as our power, it is simply that number without the radical. What does that mean? Hey, I can pull this guy all the way out the radical. It does not belong in a radical anymore. We get the single representation. The representation of this group is 2. Pull that guy out. Don't pull both of them out. Pull the representation. And now, these guys were isolated. They stay inside your radical. So they stay inside. And 2 times 3 is 6. Boom. And be careful. This is not 2 squared. This is the root 2 right here. So don't get that confused. Moving forward, let's say we have something even bigger. Let's say we have, so example, 81 x to the 4th, y to the 8th power, the 4th root of all of that. Well, let's do our factor tree. The factor tree of 81 is 9 and 9, 3 and 3, 3 and 3. Those are our only primes. So, notice that my index this time is the number 4. And because it's 4, I need groupings of the same prime numbers in groups of 4. Well, there's only 3s, but thankfully there's 4 3s, so I can circle that. Then I can rewrite this as 3 to the 4th power, and I'm going to break up x and y because some people don't know how to deal with the variables. We know this is the exact same thing. I'm saying x times x times x times x times y 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 times y. And then if I group them up in groups of 4, like I did with the prime numbers, boom, boom, boom. I get the single representation of each of them. So first, we have a 3. We have a single representation for 3. We have a single representation for x. We have a representation for y. We also have another representation for y. However, then we realize there is nothing left inside this 4th root. There is nothing left inside it. I don't need it anymore. So this is our answer. However, there's 2 y's. They're multiplying each other, so this should be 3xy squared. Since they're next to each other, they're multiplying. That was the whole point of factors, where this is all multiplication. There was no addition involved. So now we know how to simplify radicals. And I encourage you to try these out. Practice these on your own. Or kind of find some other, I guess, places where you can find practice problems. There's some in your book as well, so make sure you practice those. I will be posting up some later on. But moving on to the next section. This is a very short one. This is called rationalizing. Cool. Let's see if I forget anything. I think I forget anything. Oh, let me just talk about this real quick before I go into rationalizing. You know, this is part of the properties, but I'm hoping that you guys get the idea of it. Suppose I had two roots multiplying each other. You know, let's say root 10 times root 15. All you simply have to do is multiply the insides with each other. The inside multiplies with the inside. The outside multiplies with the outside. And the reason why is because when you take it to the exponential world, these are our bases. That is our base. So this is just going to be square root of 150. But you have to do the factor tree if you want to get that. What is that? 10. Then we do 2, 5, 3, 5. And then we circle in pairs because we assume it's squared. So circle the pairs. Boom. And then we have 5 root 6. Boom. So that's how you multiply radicals, just real quick. Now let's just get into rationalization. Which I technically didn't have to show you this because it's going to be in rationalization. But oh well. Alright, we have to know how to rationalize this guy right here. Now, mathematicians do not like dividing this out. Why? Because if we notice, this is what we call an irrational number. Irrational numbers are numbers that have decimals that never end. They never ever end. And they don't repeat. Now, 1 is a natural number. So try to imagine in your head 1 divided by some decimal that never ends. That's very hard to imagine. So it's like saying 1 divided by pi. I can't even imagine that. Now, take it the other way around though. Pi divided by 2. I might not know all the numbers of pi, but if I divide it by 2, I have an idea at least of how to do that. I have an idea how to look at pi and cut it in half. That's easy for me to visualize. So, rationalizing is keeping the same problem. However, I want the irrational number to be on top and the rational number to be on bottom, / integer / natural or whatever. So, how do I do that? I can multiply this by square root 2 over square root 2. Your denominator, whatever that irrational number is, just multiply it out. Boom. Why does that work? Well, you are not changing the value of your problem. Because square root 2 divided by square root 2, that's equal to 1. I'm only changing its representation. And in doing so, I get square root 2 over square root 2 times square root 2. We talked about how to multiply radicals. That's square root 4. And this simplifies to square root 2 over square root of 4 is 2. Boom. So that's how you rationalize, and we're done with that. Now we get to the final topic of today's lesson. 3.1. This is polynomials. We're not going to go too far into it. I'll save that for tomorrow, but polynomials. Let's suppose, or before we even go to polynomials, I have to give you some actual definitions. So definition time. Let's talk about the word term. What is a term? All a term is a component of an expression separated by addition and subtraction. Example. An expression, I'll give you the example of an expression, 2x squared, or to the 4th power, plus 3x plus, or minus 2. What is the number of terms I have? Which ones are terms? Well, they're separated by plus or minus signs. So this guy right here is separated by this plus sign. And this guy is separated by the plus sign and minus sign. And this guy. So we have, in total, 3 terms. Well, we have 3 terms. Now, with those 3 terms, we can do some mathematics with it, but I also need to formalize some other names at least. So, if I have 1 term, I can call that a monomial. Mono means 1. If I have 2 terms, I can call that a binomial. If I have 3 terms, I call that a trinomial. And anything more than 1, I call that a polynomial. So these are how you name terms or expressions. Expressions can be called polynomial, monomial, binomial, trinomial, etc. And I think this is a very good closing point right here. So we'll stop here for today, and then we'll continue on polynomial operations tomorrow. Take care.